Have you ever wondered why everything in the universe behaves the way it does? This isn't just a philosophical musing, but a question that drives the discovery of the laws of the universe. The grand tapestry of existence, from the smallest subatomic particles to the largest galaxies, follows these laws. They are the invisible threads that weave together the cosmos, the rules that govern the cosmic dance of matter and energy. Every star that twinkles in the night sky, every planet that orbits those stars, every comet that streaks across the heavens, they all dance to the tune set by these laws. Our very existence, the air we breathe, the ground we walk on, all are manifestations of these universal laws at work. Today, we're going to delve into these laws. We'll try to scratch the surface of the profound and fascinating principles that govern our universe. By the end of this video, you'll have a basic understanding of the fundamental laws that govern our universe. One of the most well-known laws of the universe is gravity. Now, gravity isn't just the reason why when we jump, we come back down. No, it's a much grander, universal concept. To understand gravity, picture the universe as a massive, flexible sheet. Now, imagine dropping a bowling ball onto the sheet. It creates a dent, right? This is how massive objects like planets distort space. Smaller objects like apples or humans are drawn towards this dent. That's gravity in a nutshell. But wait a second, how does this translate to our daily life? Well, every time you drop something, it's not that it's falling towards the earth. It's the earth that's rushing up to meet it. Surprising, isn't it? But that's the beauty of gravity. And it doesn't stop there. Gravity is the invisible glue that holds our universe together. Without it, planets would drift apart, stars wouldn't form, and we wouldn't exist. It's gravity that pulls matter together into planets, stars, and galaxies. But here's where it gets even more interesting. Gravity doesn't just affect physical objects. It also influences time itself. Near a massive object, time slows down. So a second on Jupiter would be slightly shorter than a second on Earth. It's a mind-boggling concept, isn't it? And what about the planets orbiting the sun? They're not just floating there. They're falling towards the sun, but also moving fast enough sideways to miss it. It's a bit like spinning a ball on a string around your head. The ball wants to fly away, but the string, our gravity in this case, pulls it back. So, gravity isn't just a force. It's a fundamental part of the universe, a cosmic rule that everything from the smallest particle to the largest galaxy must follow. It's an invisible hand, guiding the dance of stars and galaxies across the universe. Gravity is the force that keeps our feet on the ground and the planets in their orbits. And it's this force that makes the universe the beautiful, mysterious place it is today. Next, we venture into the world of thermodynamics. Thermodynamics, in essence, is the study of energy and its transformations. This field of physics is governed by three fundamental laws, each one shedding light on the intriguing dance of energy in our universe. Our first stop is the zeroth law of thermodynamics. Despite its slightly odd name, the zeroth law is quite simple. It states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Essentially, this law is the foundation for the concept of temperature. It's what makes it possible for us to use a thermometer to determine how hot or cold something is. Moving on, we encounter the first law of thermodynamics. This law, also known as the law of energy conservation, asserts that energy cannot be created or destroyed, only transformed. It's the reason why a car engine can convert chemical energy from fuel into mechanical energy to move the vehicle, or how a light bulb can transform electrical energy into light and heat. Finally, we arrive at the second law of thermodynamics. This law states that the total entropy or disorder in an isolated system can never decrease over time. It's this law that explains why your coffee cools down to room temperature or why a perfume diffuses throughout a room. It's a law that gives direction to the flow of time, from past to future. Each of these laws, in their own way, outlines the rules that energy must follow. They govern everything from the smallest atoms to the largest stars, and every machine or process in between. So, whether we realize it or not, these laws of thermodynamics are intricately woven into the fabric of our daily lives. They're the unseen directors guiding the transformation of energy in our cars, our homes, our bodies, and even our planet. From powering our cars to heating our homes, the laws of thermodynamics play a crucial role in our everyday lives. Now, let's delve into the laws of motion. Imagine you're standing at the edge of a pond, skipping stones. You give the stone a swift flick of the wrist, and it soars, skimming the surface before it eventually sinks. This simple act is governed by a set of rules, the laws of motion, laid out by one of the most influential scientists in history, Sir Isaac Newton. Firstly, we have Newton's first law, also known as the law of inertia. This law states that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. Like the stone you tossed, it would have stayed in your hand, at rest, if you hadn't exerted a force on it. And once it was in motion, it would have kept going if it weren't for the water slowing it down and gravity pulling it down. Next, we have Newton's second law, the law of acceleration. This law defines the relationship between force, mass, and acceleration. It tells us that the force acting on an object is equal to the mass of that object multiplied by its acceleration. So, the heavier the stone, the more force you'd need to give it the same acceleration as a lighter one. Lastly, we have Newton's third law, the law of action and reaction. This law states that for every action, there is an equal and opposite reaction. This means that when you threw the stone, the force you applied to it was also applied to you in the opposite direction. But because you're much heavier than the stone, you barely moved while the stone was sent flying. These laws of motion describe the relationship between a body and the forces acting upon it, and its motion in response to those forces. They are the fundamental principles that govern the mechanics of how objects move. From the flight of a bird to the journey of a spaceship, the laws of motion are in play. Last but not least, we come to the fascinating law of relativity. Now, if you think about Albert Einstein, you probably picture a wild-haired genius scribbling complex equations on a chalkboard. And you wouldn't be wrong, because one of his most groundbreaking accomplishments was indeed the theory of relativity. Let's break it down. What is the theory of relativity? In essence, it's all about how we perceive space and time. Einstein proposed that space and time aren't separate entities, but are interwoven into a single continuum known as space-time. Imagine space-time as a fabric. If you place a heavy object on this fabric, like a bowling ball on a trampoline, it will cause the fabric to curve around it. This is essentially how gravity works in Einstein's theory. The sun, for instance, warps the space-time around it, and this warping is what keeps the Earth in its orbit. But there's another aspect to relativity, the idea that the laws of physics should appear the same to everyone, regardless of how fast they're moving. This is where we get the idea that the speed of light is the same for everyone, no matter what. Even if you're racing at near light speed in a spaceship, light will still seem to be moving away from you at the same speed. Now, why does all this matter? Well, without the theory of relativity, we wouldn't have global positioning systems or GPS as we know them. These systems rely on time measurements from satellites, and due to a relativity, time actually ticks a tiny bit slower for these satellites than it does for us on Earth. If we didn't account for this, our GPS coordinates would be off by miles. The law of relativity has not only shaped our understanding of the universe, but also paved the way for the development of modern technologies like GPS. In the past few minutes, we have journeyed through the fundamental laws of the universe. We started with the law of gravity, the invisible force that keeps our feet on the ground and the planets in their orbits. Next, we explored the laws of thermodynamics, governing the flow of energy and the inevitability of entropy. Moving forward, we dissected Newton's laws of motion, the principles that explain how objects move and interact, from a falling apple to a soaring jet. Lastly, we delved into the law of relativity, Einstein's groundbreaking theory that revolutionized our understanding of time, space, and gravity. These laws aren't just theoretical concepts. They're the invisible threads that weave the fabric of our reality, influencing everything from the way we brew our morning coffee to the cosmic dance of galaxies. While these laws might seem abstract, they are the rules that govern our existence, making the universe the magnificent spectacle that it is.